Welcome to Math TV with Professor V. This is the root test part 2. This is a continuation to the introductory video lecture on the root test. So if you haven't watched it already, I'll link it here. I just wanted to do more spicy advanced examples in this video to give you guys a little bit more exposure and context. So just a quick recap of what the root test is. If you have an infinite series, sum of an, and the limit as n approaches infinity of, this is the nth root of the absolute value of an. If this limit is less than 1, then we say the sum of an converges. And not only does it converge, it converges absolutely. So the root test is always a test for absolute convergence because you have to take the absolute value of the terms. Second outcome, if the limit as n approaches infinity of the nth root of the absolute value of an is greater than 1, then the sum of an diverges. And last case is if the limit as n approaches infinity of the nth root of the absolute value of an is 1, then the root test fails. What does that tell us? That you chose the wrong time to use the root test. So sorry, pick another test. So it's inconclusive. It gives you no information. The series could converge or diverge. It just wasn't the time for the root test, okay? All right, so here we go. Let's look at some examples, and we're exclusively going to focus on the root test in this video to determine if the series converges or diverges. So first one I have for you is the sum, n equals 1 to infinity, of n squared plus 1 over 2n squared plus 1 raised to the n. So to start off, we're going to take the limit as n approaches infinity. It's of the nth root of the absolute value of an. Okay? Burn that in the brain. So here, I'm going to look at the limit as n approaches infinity of the nth root of the absolute value of n squared plus 1 over 2n squared plus 1 to the n. Okay, the absolute value in this particular series isn't really doing much for me because none of the terms are going to be negative anyways. N goes from 1 to infinity. There's no like alternating component. There's no negative 1 to the n. I'm not finding a radius of convergence. There's no x's in here, so I can drop them after this step, all right? So continuing on, now we have the limit as n approaches infinity. If I take the nth root of something that's being raised to the n, then that's going to cancel out. Remember, when you take the nth root of x, that's the same as raising it to the 1 over n. So that's why if you already have something raised to the nth power, then those will cancel out. The reason we have to take the absolute value, though, is to be careful that x isn't going to be negative in the end, okay? Good. Let's get this out of the way. So now we're going to be left with n squared plus 1 over 2n squared plus 1. Okay, great. So n is approaching infinity. I notice the numerator is going to infinity. Denominator is also going to infinity. So what I'm going to do is divide by the highest power of n from the denominator, which in this case is n squared. So I'm going to divide everything by n squared. And then now we have the limit as n approaches infinity. Distributing that through the numerator, I'm going to have 1 plus 1 over n squared. And then in the denominator, we're going to have 2 plus 1 over n squared. All right, so now we should be able to evaluate that limit, right? Can you guys see it? So as n approaches infinity, 1 over n squared, that's going to 0. Same thing for here. And all I'm left with in the numerator is a 1. And in the denominator, I have a 2. So this limit equals 1/2. Now, what do I care about 1/2? What do the conclusions of the root test tell me? Well, if this limit is less than 1, then this tells me that my original infinite series, n equals 1 to infinity, Yes, you should always rewrite it. 2n squared plus 1 over 2n squared plus 1 to the n. This series is absolutely, I'm putting it in parentheses because they didn't ask for that, but we know it is absolutely convergent by the root test. Always say what test you used. In this case, we're exclusively focusing on the root test, okay? But when you're just given a series and you apply some test, you should specify at the end which one it was you used, okay? How was that one? Not too wild. I know that was a warm-up one. So here we go. Now we're going to get into the good stuff. Example number 2. We've got here the sum, n equals 1 to infinity, of 1 plus 1 over n raised to the n squared. Ooh, okay. So remember, we're going to look at the limit as n approaches infinity of the nth root of the absolute value of 1 plus 1 over n to the n squared. And again, I don't need the absolute value. The only terms in here that are variables are n. They're going to infinity. They're starting at 1. They're not negative. So we've got the limit as n approaches infinity. And I'm going to rewrite this as 1 plus 1 over n to the n squared. And instead of writing the nth root that way, I'm going to write this whole quantity raised to the 1 over n so that you can see how to clean it up, okay? Now, do you remember our rule for simplifying exponents when you have a power raised to another power? So if you have x raised to the a raised to the b, that ends up simplifying as x raised to the a times b. So you multiply those exponents. You're going to multiply n squared by 1 over n. And what would that give us? Just n, right? Okay, good. So this is where we're at. And then let's see. Some of you might recognize this expression. This is a famous limit and already know what it equals. If it does, that's great. Most of my students don't remember what this is, so I'll show you how we evaluate this limit if you don't happen to recognize it. Okay, first thing that's important though is as n goes to infinity, 1 over n is going to go to 0, right? And this is not, I'm sorry guys, this limit is not equal to 1, okay? That's probably the most common illegal little phrase I hear coming out of my students' mouths. The base, right, in this limit is approaching 1 and the exponent is approaching infinity. This is an indeterminate form of the type 1 to the infinity. It's not equal to 1, guys, okay? No. The exponent is approaching infinity. The base is approaching 1. So if you remember, when you have an indeterminate form of this type where it's an indeterminate power, we have to apply Lhopitals Rule and bust out a natural log in order to do so. If you forgot about this technique, I'll link the video here where I go over Lhopitals Rule. Fast forward closer to the end when we do the indeterminate powers. And there's 7 indeterminate forms. In case you've forgotten them, I'll just recap them. The indeterminate powers, there's 3 of them. 1 to the infinity, infinity to the 0, 0 to the 0. And then the ones that you can use Lhopitals Rule on are infinity over infinity or 0 over 0. And then there's 2 more, infinity minus infinity, and then 0 times infinity. So there's 7 of them. Just think there's 7 deadly sins, there's 7 indeterminate forms, and these are their types. So be on the lookout, okay, so you don't do something illegal. This is the one that we're going to focus on right now. Okay, so what to do? Well, off to the side, just say we're going to consider the limit. And yes, I'm switching to x as x approaches infinity of 1 plus 1 over x to the x. Why am I doing that? Because you can only apply Lhopitals Rule to differentiable functions, and a sequence is definitely not differentiable. It's not even continuous. And in fact, I'm going to take this original limit that we're interested in and add a natural log in the front. You'll see why in just a second. Okay, so anytime you're going to try to use Lhopitals rule for an indeterminate form of this type, add a natural log in the front. Why? So that you can move this exponent down in the front here. So now we've got the limit as x approaches infinity of x times natural log 1 plus 1 over x. And remember, you're only allowed to use Lhopitals rule on indeterminate forms of the type infinity over infinity or 0 over 0. So I'm going to try to rewrite this limit here, this expression, as a quotient instead. And usually you leave the natural log part where it is. You're just going to flip the x to the denominator. So I'm still going to have ln 1 plus 1 over x. And then I'm just going to rewrite x as 1 over x in the denominator. Same thing, right? Okay, but now I'm super happy because I have an indeterminate form of the type 0 over 0. So I can apply Lhopitals rule. How did I notice that? Well, 1 over x, we already said that's going to 0. So in the numerator, I just have natural log of 1. What's natural log of 1, you guys? It's 0, right? And then as x is approaching infinity, this denominator, that's also approaching 0. So we have an indeterminate form of the type 0 over 0. So yay, we can go ahead and apply Lhopitals rule. So you got to let everybody know that's what you're doing. Bam, you write a little LH over your equal sign there. And then we've got the limit as x approaches infinity. Don't worry, I'll remind you how to do Lhopitals rule right now. You take the derivative of the numerator, and then you take the derivative of the denominator, independent of one another. Don't do some quotient rule shenanigans right now. So derivative of natural log of 1 plus 1 over x, derivative of natural log of something is always 1 over the something, and then you have to apply the chain rule and multiply by the derivative of the something, right? Of whatever the argument was of the natural log. So derivative of 1 is 0. Derivative of 1 over x, that's x to the negative first, right? So derivative would be negative x to the negative second, or negative 1 over x squared. Okay, so that's the derivative of the numerator. Derivative of the denominator, the derivative is just going to be same thing as we had up here because it's just x to the negative first, so it'll be negative 1 over x squared. Okay, I know it looks messier, but things will work out for us in just a second. Notice these negative 1 over x squareds cancel out. Love it. And then let's see if we can evaluate this limit now. So we've got the limit, x approaches infinity, 1 over 1 plus 1 over x. So as x approaches infinity, 1 over x approaches 0, and I'm just left with 1 over 1, which is 1. Okay, great. So now we've evaluated this limit. But remember, this was the limit of the natural log of 1 plus 1 over x to the x. That's not originally the limit that we wanted. Our limit didn't have a natural log in it. So just think, what is the inverse function for natural log of x? It's e to the x. So this means the limit as x approaches infinity of e to the ln of 1 plus 1 over x to the x would be e, and then just pass that limit through to the exponent, to the limit as x approaches infinity of ln of 1 plus 1 over x to the x, and we just showed this whole limit goes to 1. So our final result is e to the first, which is e. So then that means the limit as n approaches infinity of 1 plus 1 over n to the n is also equal to e. Okay, good. So just recall e to the ln of y is just equal to y. That's why we took that limit with the extra natural log in it, and then had e raised to that result. Anyways, end of the day, we got the limit, woo-woo, and it's equal to e. What do I care about e? Well, what test am I doing again? You probably forgot. We're doing the root test, you guys. And the root test, you always compare your result to 1. Well, e is about 2.71, yada, 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 which is more than 1 for sure. So this tells me that my original series, the sum n equals 1 to infinity, 1 plus 1 over n to the n squared, that diverges by the root test. Okay. Fabulous. I have one more for you. Yeah, that's it. Honestly, the root test is a little outshined by the ratio test in practice. We use the ratio test a lot more. We have the sum, n equals 1 to infinity, 6n to the 1 over n minus 1 over, oh, you know what? I have it written down here. Why am I rewriting things? We have the sum, n equals 1 to infinity, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1, and then all of that raised to the n. Okay, let's get going then. We've got the limit as n approaches infinity of the nth root of absolute value, parentheses, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1, all raised to the n. Okay, as we discussed, taking the nth root is the same as raising a quantity to the 1 over n. So these guys just can cancel out if you want to write it out that way. And then I'm not going to keep writing the absolute value bars because everything's going to be positive. So we've got the limit, n approaches infinity, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1. All right, let's see what's happening. As n approaches infinity, where's n to the 1 over n going? The base n is going to infinity, and 1 over n is going to 0. And now, you're not a sloppy little calculus student. You recognize this is an indeterminate form of the type infinity to the 0. Indeterminate, okay? So you must use Lhopitals Rule to evaluate this limit. You're not just going to be like, oh, it's 1 because anything to the 0 is 1. No. No, no, no. Okay. So off to the side, you just do a little consider. I'm going to change everything to x's because I know I have to use Lhopitals Rule. And I'm going to throw the ln in right now. So consider the limit as x goes to infinity of ln of x to the 1 over x. Remember, we use the natural log so we can rewrite the indeterminate limit in the form infinity over infinity or 0 over 0. So move that 1 over x to the front. So now we've got the limit, x goes to infinity, 1 over x times ln of x. I mean, I could just put the x in the denominator now, right? And we've got ln of x over x. And sure enough, yeah, numerator's going to infinity, denominator's going to infinity, so we're allowed to use Lhopitals Rule. Tell everyone that's what you're doing. Don't act like it was your idea. So then we have the limit as x goes to infinity. Derivative of the numerator. Derivative of ln of x is 1 over x. And then the derivative of the denominator, x, is just 1. So now we just have the limit, x goes to infinity, 1 over x, which is 0. Okay, that's not the original limit that we were after, though. Remember, we added in the natural log? So that means the limit as n approaches infinity of n to the 1 over n without the natural log. Do you remember how we got rid of it last time? You take e and raise it to whatever result you got previously with the natural log, basically to undo it, right? And then this is going to be e to the 0, which is 1. Okay, that's not the limit though of the expression in the root test. That's just the limit of this little quantity right here. So we know n to the 1 over n, that goes to 1. Okay, so let's just continue what's going on right here below so we can finish up. That's going to 1. Again, this n to the 1 over n will be approaching 1 also. So in the numerator, I'm going to have 6 times 1 minus 1. Denominator, 3 times 1 minus 1. So this is 5 over 2. What do I care about 5 over 2? I'm doing the root test. I compare everything to 1. 5 over 2 is greater than 1. So this tells me my original sum, n equals 1 to infinity, 6n to the 1 over n minus 1 over 3n to the 1 over n minus 1 raised to the n diverges by the root test. Okay, so I hope you found this video helpful. This sort of indeterminate form comes up a lot when you use the root test. If in some circumstances, you're doing the ratio test, it doesn't come up so often, but all of these series required the root test, so it couldn't be helped. Subscribe if you haven't already to my channel and share it with your classmates. I'm sure they'll benefit from it too. If you have any topics that you can't find on my channel, let me know. I'm always a busy bee, but I'm happy to take video requests, and I'll see you guys soon.